Welcome to ScaleUp University. Welcome to the course on linear algebra and learning from data. So this is the module 1, lecture 1, and in this lecture we will be discussing why linear algebra for learning from data. Like in this lecture we will see how linear algebra helps us in learning from data. Why linear algebra is a perfect mathematical tool that enables us to learn from data. So that is what this lecture is about. So in this lecture, we will look at some very important topics like algebra as the language of artificial intelligence, from equations to vectors to matrices to data. We'll look at the importance of the central equation of linear algebra, that is Ax is equals to B, applications of linear algebra in machine learning, optimization, compression, and finally we will discuss why large matrices matter. So all these topics we will cover in this lecture itself one by one. So first we'll start with the first topic. So this is the module 1, highlights of linear algebra, lecture 1, why linear algebra for learning from data, and we are starting with the first topic, that is linear algebra as the language of artificial intelligence. So if we talk about linear algebra as the language of artificial intelligence, first we will discuss why study linear algebra today. See, the modern world, it runs on data, and linear algebra is the math of data. If we talk about linear algebra, it is the math of data. Linear algebra provides the essential language for representing multidimensional information and the computational framework for processing data at scale. So now it's very clear to us that in the modern world, we are dealing with the data and we need some mathematical tools so that we can efficiently handle that data. We can represent that data. We can process that data in an efficient manner. And linear algebra is that tool. So linear algebra is that tool using which we can represent multi-dimensional information. And linear algebra, it also provides us the computational framework for processing data at scale. So now we are getting or we are realizing the significance of linear algebra, especially how it is a perfect tool in dealing with data, in processing data, in managing data. So every major technology today, it depends on linear algebra. So any major technology you take, it has something to do with the linear algebra. Like if I talk about artificial intelligence, machine learning, deep learning, so these all, they make use of linear algebra. So artificial intelligence, machine learning, deep learning. So linear algebra is the bedrock of artificial intelligence, machine learning, deep learning. And linear algebra, it is used from data storage to actual learning process. So in the field of AI, ML, and deep learning, we use linear algebra to represent the data. We use it for data representation. So all the different forms of data, like the images, text, audio, it is converted into vectors, that is the list of features, and matrices, that's the data sets for computers to process. So in AI, ML, and deep learning, whatever the data we have, that data can be the text data, textual data, images, audio, we convert that data into vectors and matrices, and then we compute it. So, if we are talking about vectors and matrices, we are talking about linear algebra. So linear algebra is used for data representation in AI, ML, and deep learning. And similarly, linear algebra is used for model training. So in neural networks, learning involves repeatedly multiplying input vectors by large weight matrices. And that multiplication of input vectors by large weight matrices is carried out using the principles of linear algebra. And hence, linear algebra plays a role in model training. So the idea is that we have a data, like the input data, we have the weight matrix. Now using the principles of linear algebra, we multiply the data, the input vector with the weight matrix to get some prediction vector. So we carry out the matrix multiplication, which is a concept of linear algebra. Linear algebra, it is also used in AI, ML, and deep learning for optimization. So optimization is like minimizing the cost function, minimizing the error. So techniques like gradient descent, it uses linear algebra to adjust weights, minimizing errors, and improving the model accuracy. So now it's very clear that in the field of artificial intelligence, machine learning, and deep learning, linear algebra plays a very, very important role. Linear algebra is used to represent the data, whether you are dealing with the textual data, you're dealing with images, or you're dealing with audio. We convert those data into vectors and matrices before further processing it. So linear algebra has a role to play in data representation. In the field of AI, machine learning, and deep learning, linear algebra plays a role in model training. So we multiply the input vector with the weight matrices. So that matrix multiplication is taken care by the principles, the concepts of linear algebra. And also linear algebra also plays a role in optimization. Like in AI, ML, and deep learning, we use gradient descent as one of the optimization technique, and that gradient uses gradient descent, it makes use of linear algebra to adjust weights, minimize errors, and improve the model accuracy. So linear algebra, it also plays a role in recommendation systems and search engines. So linear algebra is used in recommendation systems and search engines. So modern web platforms, they rely on matrix operations to organize the internet and predict what you will like. So in search engines, matrix operations are used. In recommendation systems, operations are used. So if we talk about search engines, and in search engine also, uh, we are mainly emphasizing on the page rank. So in search engines, especially the page rank, Google, it represents the web as a massive adjacency matrix where links between pages are entries. So companies like Google, like we all use Google search. So Google search, it represents the web as a massive adjacency matrix wherein the entries of these matrices is the link between these web pages. So finding the most important pages is mathematically equivalent to finding the dominant eigenvector of this matrix. So Google search or any search engine you consider, if we are talking about the page rank algorithm of Google search, it makes use of the adjacency matrix to represent the web pages. So the entries of adjacency matrix is the links. So wherever there is a link between the web pages, that will be an entry in the adjacency matrix, and we find the most important pages mathematically using the linear algebra using the concept of eigenvector. We find the eigenvector of this adjacency matrix which will give us the most important pages, and hence we are making use of linear algebra here. Similarly, in recommendation systems also, we make use of linear algebra. So recommendation systems, you know that we have seen recommendation engines like any e-commerce platform. If you visit, it recommends you some products. If you explore an OTT platform like Netflix, it recommends you movies. If you visit LinkedIn, it will recommend you connections to follow. So that is what recommendation engine is. So in recommendation systems, like services like the Netflix, it uses collaborative filtering. So companies like, or the products like the Netflix OTT platform which we use, it makes use of the collaborative filtering, which involves factorizing a large user item matrix into small feature matrices to predict missing ratings. So this is called as matrix factorization. So basically in collaborative filtering, Netflix, what it does is that it uses the user item matrix, like based on the past behavior of the user, what items the user preferred. So making use of the user item matrix, it factorizes a large user item matrix into two smaller feature matrices. So these are like the feature matrices. So we have a matrix called user feature and an item feature. So a large user item matrix is factorized into a user feature matrix, a smaller user feature matrix, and a smaller item features to predict the missing ratings. And here also we are making use of matrices, and hence we are making use of linear algebra. So now we are realizing the importance of linear algebra, that linear algebra not only in artificial intelligence but also in recommendation systems and search engines, linear algebra plays a very big role. Similarly, linear algebra do play a role in computer vision and robotics. In computer vision and robotics, linear algebra plays a very big role. So computer vision and robotics, they use linear algebra to translate physical word geometry into digital coordinates. So if I talk about computer vision in particular, so in computer vision, digital images are stored as matrices of pixel values. So in computer vision, we represent digital images as matrices of pixel values. Operations like the edge detection, blurring, or rotating are performed by applying linear transformations, that is a matrix multiplication, to these pixels. So the operations on the image is basically the linear transformations of these matrices. So the idea is that in computer vision, we represent digital images as matrices, like we represent it as a pixel matrix, a matrix containing the pixels. And the operations on these images, like the edge detection, blurring, and rotating, is basically the linear transformations on these pixel matrices. So hence, computer vision heavily makes use of linear algebra, because whenever we are talking about matrices, we are talking about linear transformations, we are talking about linear algebra. So linear algebra is used to represent digital images and also to process digital images. Similarly, in robotics, if we talk about robotics, in robotics, engineers, they use homogeneous transformation matrices to model a robot's pose, that is a position and orientation. So the modeling of a pose of a robot is done using homogeneous transformation matrices, which is a concept of linear algebra. Even like solving inverse kinematics, like calculating how joints must move to reach a specific point, is a complex system of linear equations. So in inverse kinematics also, it involves complex systems of linear equations, which is a part of linear algebra. So now it's very clear that if we talk about linear algebra, it has applications in computer vision and robotics. In computer vision, we represent digital images in the form of matrices, pixel matrices, and processing of image is basically the linear transformations performed on the pixel matrices. Similarly, in robotics, we use homogeneous transformation matrices to model a robot's pose, and to solve inverse kinematics, we make use of complex systems of linear equations, which is a part of linear algebra. So linear algebra, it also has a role to play in scientific computing, signal processing, and beyond. So linear algebra do have a role to play in scientific computing, signal processing, and beyond. So linear algebra provides the heavy lifting for complex simulations and data analysis. So if we talk about scientific computing, so linear algebra plays a role in simulating physical phenomena. So simulating physical phenomena like the weather, fluid dynamics, it requires solving millions of simultaneous linear equations, often using LU or QR decomposition for efficiency. And which are the concepts of linear algebra? So linear algebra, it is used in scientific computing. So when we are simulating physical phenomena like the fluid dynamics, weather, it requires solving millions of simultaneous linear equations. And to solve those millions of simultaneous linear equations, we make use of the concepts of linear algebra like the LU or QR decompositions. Linear algebra also has a role to play in signal processing. So in signal processing, techniques like the fast Fourier transforms, which is also used in Wi-Fi and audio compression, are rooted in linear transformations that convert signals between time and frequency domains. So if we talk about signal processing, in signal processing, converting the time domain into the frequency domain and vice versa is very important. So the fast Fourier transforms, they make use of linear transformations, which is a concept of linear algebra. So linear algebra do play a role in signal processing also. So the fast Fourier transforms, like conversion from a time domain to frequency domain, it makes use of linear transformations. And linear algebra also plays a role in dimensionality reduction. So principal component analysis, it uses eigenvalues and eigenvectors to compress high dimensional data, keeping only the most important features. So the idea is that, let us suppose we have some high dimensional data. Now using the principal component analysis, like which makes use of the eigenvalues and the eigenvectors, so we can reduce the dimension. So, so dimensionality reduction we can do using the principal component analysis, which further makes use of eigenvalues and eigenvectors, which is a concept of linear algebra. So now it's very clear to us that, okay, if we talk about scientific computing, signal processing, and beyond, like dimensionality reduction, linear algebra plays a role. In scientific computing, like if we are simulating physical processes, it involves solving millions of simultaneous linear equations. We make use of the concepts of linear algebra like the LU or the QR decompositions. In signal processing, we do the conversion of the time domain to the frequency domain. We make use of something called as fast Fourier transforms. It uses linear transformations, which is a part of linear algebra. And also in dimensional reduction, we make use of principal component analysis, which uses eigenvalues and eigenvectors to compress high dimensional data into important features. So this eigenvalues and eigenvectors is a concept of linear algebra. So linear algebra is the hidden engine behind AI. Linear algebra is the hidden engine behind AI. So if we look at like what powers the modern AI, data as geometry. So in the world of AI, data isn't treated as text or images. It is treated as geometry. Because you know that in artificial intelligence, we try to find the patterns in the data. And if we are trying to find the patterns in the data, we are considering data or we are treating the data as geometry and not as text or images. So in the world of AI, we treat data as geometry to identify patterns in it. So that is what is the core philosophy behind the modern AI, finding patterns in the data. So if we treat data as geometry, it is possible for us to find the patterns. And to treat data as geometry, linear algebra plays the role. So linear algebra is the framework that allows computers to see patterns in high dimensional space. So we can see patterns in high dimensional space using linear algebra. Linear algebra is the framework. So if we talk about the core components of linear algebra, which powers the modern AI. So the core components is the how. So we have vectors. So vectors are the basic building blocks. Every piece of data, like a word, a pixel, or a user preference, is converted into a vector. So vector, you can treat it like a list of numbers. Now that list can be a horizontal list or a vertical list. So we can have a row vector, we can have a column vector. So list of numbers is a vector. So basically, whether we are talking about a word, a pixel, or a user preference, like every piece of data is converted into a vector. So this places the data at a specific point in multidimensional embedding space where similar items are mathematically closer. So what we do, if we represent the data in form of vectors, then in a multidimensional embedding space, automatically we will see that the items which are related to each other, which are closer to each other, mathematically also they will be close. Like let us suppose if we have data related to dog, so it will by default be occupying, it will be close in this region, and the data points related to cat will be falling in this region. So if we represent the data as vectors, then because of that, automatically the vectors in a multidimensional embedding space, similar items, they will fall closer. They will be mathematically closer to each other. And hence, this is a very powerful concept which enables us to find patterns. And now, see, we already saw that with linear algebra as a frame. So, linear algebra is the framework to represent data as geometry. And now we are getting a feel of it. Because if we represent the data as vectors, by default, similar items, they will be mathematically closer to each other. So we are treating data as geometry. So if we talk about the core components of linear algebra, we have matrices. So the core components of linear algebra which powers the modern AI, matrices is one of the core component. So you can think of matrices as the memory of the AI, the AI's memory. A matrix is a collection of vectors. And since it's a collection of vectors, matrix represents a data set. In a neural network, the weight matrix stores everything the model has learned. So in neural networks, we may use of something called as the weight matrix, which represents everything which the model has learned. So weight matrix stores the learned information. So when you input data, it interacts with these weights. So input data interacts with these weights in the weight matrix. Now the next core component of linear algebra powering the modern AI is the transformations. So see, vectors and matrices, it is more of like representation. Vectors and matrices, they are used to represent the data, but transformation is the action, processing the data. When an input vector is multiplied by a weight matrix, it undergoes a linear transformation. So whenever we multiply a input vector with a weight matrix, then the result is a linear transformation, and that transformation can be rotation, scaling, shearing, and this allows This transformations allows the AI to filter out noise and highlight relevant features. So whenever we perform operations on the vectors and matrices, whenever we perform operations, we are basically performing the linear transformations. And with this linear transformations, we can filter out the noise, we can highlight the relevant features, and so on. We also have a core component called optimizations. So optimization is also a core component of linear algebra which powers the modern AI. So see, AI, it learns by minimizing the error. Artificial intelligence, it learns by minimizing the error. So optimization makes use of calculus plus linear algebra. So by calculating the gradients, the system exactly determines how to nudge the numbers in a matrix to make the output more accurate. So that is what the gradient descent is, which is an example of a optimization technique which makes use of both the calculus and the linear algebra. So linear algebra also plays a role in optimization. So by calculating the gradients, we can find like how exactly we should update the numbers in the weight matrix to make the output more accurate. So if we talk about the core components of linear algebra, so eigenvalues and eigenvectors is also a core component of linear algebra which powers the modern AI. Eigenvalues and eigenvectors. So eigenvalues and eigenvectors, they identify essential directions in data. They tell the AI which features are the most important. They show most important features. For example, if we talk about facial recognition, eigenvectors are basically the eigenfaces, represent the most distinct features that separate one face from another. So eigenvalues and eigenvectors are like some very powerful components of linear algebra. They identify essential directions. They show the most important features to consider. Like if I talk about facial recognition, in a face, we can have so many features. But if we make use of eigenvectors, then we will have eigenfaces. So eigenfaces are the faces containing only the most relevant features, eliminating all the noise, all the unnecessary features, we are getting rid of it. So that is what eigenface. And eigenface, we can get it using the eigenvectors. Similarly, singular values, like singular value decomposition, is also a core component of linear algebra which powers the modern AI. So this is the ultimate tool for compression and noise reduction. So if you are talking about compression and noise reduction, then singular value decomposition is the ultimate tool. Singular value decomposition allows a system to take a messy matrix and break it down into its most important parts, discarding the junk data without losing the core information. So singular value decomposition, it's a technique of linear algebra which breaks down a messy matrix, discarding the junk data and keeping the core information. So now we looked at the core components of linear algebra. Now we will look at the functional benefits of linear algebra, the why. Like why we should use linear algebra, or why linear algebra is powering the modern AI. The functional benefits of the linear algebra, like why we should use linear algebra, or why the linear algebra is powering the modern AI. So representation. So linear algebra provides a universal language. Whether you are translating French to English or identifying cancer in a X-ray, So whether you're translating, identifying, doing some kind of a recognition, linear algebra represents both problems as operations on numerical arrays. So linear algebra provides a universal language for representing the data. So regardless of the operation you are performing, if you represent the data in the form of vectors and matrices, you can solve problems. So that is what the linear algebra is. So now it's very clear that why linear algebra powers the modern AI, because linear algebra provides the universal language to represent the data. Computation. If we talk about modern hardware like the GPUs, they are specifically designed to do one thing extremely well, that is the matrix multiplication. So modern hardware, they make use of like GPUs. So GPUs are designed for matrix multiplication. GPUs are designed to carry out billions of simultaneous calculations. So linear algebra allows us to perform billions of calculations simultaneously rather than one by one. So now it's very clear to us that linear algebra, why it powers the modern AI, because it provides the universal language to represent the data. It provides the computational framework, because modern hardware like the GPUs, they make use of linear algebra, they make use of matrix multiplication to carry out billions of simultaneous calculations. Structure. So linear algebra, it turns chaotic data, unstructured data into a rigid geometric grid. Because with linear algebra, we are treating data as geometry. So linear algebra, if we represent the data using the concepts of linear algebra, then we are turning the chaotic unstructured data into a geometric grid. This structure allows us to use concepts like distance and angle to find invili- relationships between data points that would be invisible to human eyes. So once we convert the chaotic unstructured data into a geometric grid, we can use concepts like distances and angles to find the invisible relationships between the data points. And this is how the linear algebra is powering the modern AI. And also, we have efficiency. So, techniques like dimensionality reduction using SVD, PCA, like singular value decomposition, or the principal component analysis, it allows the AI to process massive data sets by focusing only on the components that matter, drastically reducing the amount of memory and power required. So dimensionality reduction is also a concept of linear algebra. So with linear algebra, we can also achieve efficiency, wherein we can process massive data sets by drastically reducing the amount of memory and power required. So now it's very clear to us that why linear algebra is powering the modern AI. Linear algebra provides the universal language to represent the data. It provides the computational framework like the matrix multiplication, using which modern hardware like the GPUs can carry out billions of simultaneous calculations. Linear algebra provides structure, like it can turn a chaotic unstructured data into a geometric grid structured data. Using linear algebra, we can treat data as geometry, which allows concepts like distance and angle to find invisible relationships between the data points. And linear algebra, it also provides efficiency, wherein we can use the concepts of dimensionality reduction to process massive data sets using reduced memory and power consumption. And hence, linear algebra is the hidden engine behind artificial intelligence. Linear algebra is the language of data. Data is naturally matrix shaped. See, in the modern digital landscape, data isn't just stored in tables, it is mathematically defined by its arrangement. This matrix shaped nature of data allows computers to apply mathematical operations to real world concepts. Let us look at some examples to get a feel of it, like how data is naturally matrix shaped. Let us try to understand it. So, if we talk about student marks, so we can represent student marks in the form of a matrix. So, rows will be the students and columns will be the subjects. Like student 1, maths, physics, chemistry. So, columns will be the subject, subject 1, subject 2, subject 3, and rows will be the student. So, we can represent the student marks in the form of matrix. Similarly, if we talk about images, the pixel matrix, the pixel intensity matrix is a matrix representation of an image. If I talk about Netflix recommendations, we can represent Netflix recommendations using something called as user item matrix. User item matrix. We can represent neural networks in the form of weight matrices, and social networks we can represent using something called as graph adjacency matrices. So now it's very clear that data is naturally matrix shaped. Any sort of problem you talk about, you can represent it in the form of matrix. Now all these we can discuss in some more detail. If I talk about student performance, which is a tabular data. So we already saw that. So here the problem is managing and comparing academic performance of thousands of students across multiple subjects. Just imagine we are considering a college containing thousands of students. So now the problem is to manage and compare academic performance of thousands of students across multiple subjects. And here the matrix can solve the problem. So we can have a M cross N matrix where rows represent the individual students and the column represents the subject. And what advantage we get if we use this matrix to find the average grade for a subject, perform an operation on the column vector. To find a student's GPA, operate on a row vector. So in this matrix, the row vector will give us the performance of a particular student, and the column vector will give us the performance of the entire college for a particular subject. So that can be a very powerful tool. Similarly, if we talk about digital images, the visual data, now the problem is computers, they don't see shapes, they can read numbers. Because computers, if you talk about, they can only understand numbers, they cannot see shapes and all. So we need a way to represent images in the form of numbers, and we have pixel matrix, pixel intensity matrix. So a grayscale image is a single matrix with pixel intensities 0 to 255. A color image is a 3D tensor. So it is a stacked matrix. So we will be having a 3D tensor, a three stacked matrices for red, green, and blue. So now it's very clear that we can represent a image in the form of a matrix. If it is a grayscale image, one matrix is enough. And if it is a color image, we have to use a 3D tensor. So three matrices we stack on top of it. Like we have a matrix for the red, for the green, and for the blue. And why it works? Applying a filter like in Instagram or Photoshop is mathematically multiplying the image matrix by a smaller kernel matrix. So now with this image matrix, we can perform operations on it. To process the image, we should process the matrix. So if we talk about Netflix recommendation or Amazon recommendation, we have user preference data. Now the problem is predicting what a user will like based on the past behavior and some other factors. Now, if we make use of a massive user item matrix where rows are the users and columns are the items. It can be movies for Netflix or products for Amazon. Now, how this user item matrix can play a role in predicting what a user will like. So, this user item matrix is a sparse matrix. Like in this, most cells are empty. So, AI uses matrix factorization to fill in the blanks, identifying hidden patterns. We call it the latent factors, like prefers sci-fi movie, like science fiction movie, or 90s nostalgia. So if we represent the user preference data in the form of a matrix, like a user item matrix, then we can perform some matrix factorization, which can enable us to identify hidden patterns, the latent factors, using which we can recommend movies or the products to the users. So now we are getting a realization like linear algebra is the language of data. Like how if we represent the data in the form of matrix, we can make use of linear algebra to solve problems. Similarly, if we talk about neural networks, intelligence data. So in neural networks, the problem is how does a machine store the relationship between an input and an output? Because see, the idea is that in neural network, it is a supervised learning. In neural network, what we do is that we know both the input and the output. We know both the input and the output. We give input to the neural network and it learns the pattern. So neural network, what it does is that it learns the relationship between the input and the output. It predicts the unknown function which can transform our input to an output. So in neural network, we know both the input and the output. Neural network learns the relationship. Now the problem is how it will store the relationship. So to store the relationship, if we make use of the matrix, like the weight matrix, every connection between neurons in a model has a numerical weight. So if we assign so we know that every connection among the neurons has got a weight, a numerical weight. And if we store that weight in something called as weight matrix, our problem will be solved. And let us see how our problem will be solved. So see, processing information is essentially a long chain of matrix multiplications. This is why GPUs are so vital. They are built to multiply matrices incredibly fast. So if we represent the relationships in the form of weight matrix, then computation will be very efficient because GPUs, they are made for to carry out matrix multiplications, to carry out billions of operations simultaneously. And that is possible. And this is the reason, like if we talk about deep learning or the deep neural networks, there the weight matrix can be very big. But with GPU, we can carry out billions of simultaneous operations. And this is where linear algebra is playing the role in neural networks. Social networks. So social networks, we are dealing with the connection data. Now the problem is mapping billions of relationships like the friends, followers, likes to see how information spreads. Now if this relationship we represent it in the form of an adjacency matrix, like if user A follows user B, cell A comma B is 1, otherwise it is 0. So that's the concept of adjacency matrix. So if we make use of the adjacency matrix to map the relationship, then what benefit we will get? Squaring the matrix tells you who is a friend of a friend. It turns sociology into a problem of graph theory and linear algebra. So the idea is that with matrix, if we represent the connection data of a social network in the form of an adjacency matrix, then using linear algebra, we can carry out certain interesting operations. We can square that adjacency matrix to get who is a friend of a friend. So we can turn sociology into a problem of graph theory and linear algebra. So now it's very clear that data is naturally matrix shaped. So if we represent the data in the form of a matrix, we can get some special benefits that we saw. So the key insight that we can take away from all this discussion we did, modern data problems are matrix problems. The modern data problems we are dealing with are basically the matrix problems. We no longer treat data as isolated snippet of information. By viewing the data as a matrix, we gain the ability to use linear transformations. We can rotate, scale, and project that data to find features that are otherwise invisible. If you can turn a problem into a matrix, you can solve it with a computer. So if we are talking about computation, if we are talking about GPU, then we have to treat the data as a matrix and not as a isolated snippet of information. If we can turn a problem into a matrix, we can solve it efficiently using a computer or a GPU. So modern data problems are matrix problems, and hence if there is a matrix, there will be linear algebra. So we can say that modern data problems are problems of linear algebra. From numbers to data science, evolution of mathematical thinking. So if we talk about the evolution of mathematical thinking, it represents a shift from measuring objects to measuring relationships and finally to measuring entire systems. Because we started the mathematical journey by measuring objects. Then we started looking into measuring relationships. And now we are measuring the entire systems. So this progression is what allowed us to move from simple counting to building artificial intelligence. So if we talk about the evolution of mathematical thinking, it started with the step one, the numbers, the scalars. So it was all about measuring a single isolated quantity at a specific moment, like measuring the coordinates of a point in space or the temperature. Now, the limitation of this approach is that a single isolated quantity, a number, it has a magnitude but no direction or context. It is a point in a zero dimensional space because if we are talking about single isolated numbers, they are representing just the magnitude, no direction or context. For example, if I talk about the temperature is 32 degrees Celsius. So we are measuring the temperature with a single isolated quantity 32. Now this number is giving us an idea about how hot the object is, but it tells you nothing about the wind, humidity, or how the weather is changing. So that is what the numbers. So we started our mathematical journey, the mathematical thinking by measuring objects. And to measure objects, we just dealt with numbers, the scalars, single isolated quantities. Then we came across equations, the variables. So equation means dealing with the relationship between the numbers. So equations, the concept is the rule or the relationship between the quantities. So identifying a rule or a relationship between two or more quantities is what the equation is. Then we started measuring the relationships. the rule or the relationship between two or more quantities. Now, the limitation of this step, the equations, is equations usually solve for a static unknown. They describe a balance like a scale. So for static scenarios, equations are well and good for static unknowns. But what if we are trying to analyze a dynamic system wherein the relationship is also changing? If the relationship is static, we can make use of equations to deal with it. But if the parameters are changing, then we will be needing something called as calculus. We have to measure the change. So at that time, there was no calculus. So that is the limitation of equations. It is good for solving static unknowns. So if the quantities are not changing with time, then equations are good. But if the quantities are changing with time, then these equations will no longer be valid. Like if we talk about an example, like 2x plus 3 is equals to 7. Let us say this is a linear equation. Now, in order to satisfy this, what should be the value of x? If x is 2, then this equation is satisfied. So we are discussing the evolution of mathematical thinking, and the step 3 in the evolution is the vectors, which are basically the list of numbers. Now let us understand the core concept of vectors. So grouping multiple related quantities into a single mathematical object. So the core concept of vector is basically grouping related quantities into a single mathematical object. This is where geometry enters the picture. This is where geometry enters the picture. So here we are treating data as geometry. Here we are talking about pattern. So in vector, what we do, we group related quantities into a single mathematical object. And what benefit we get is a vector represents state or direction in a multi-dimensional space. So if we talk about vectors, vectors contains numbers as well as it also represents a direction or a state in a multi-dimensional space. So that's the power of vector. So instead of just temperature, a weather station uses a vector. And if the weather station uses a vector, it will make use of a mathematical object like this, which will contain information about the temperature, the wind, the humidity. So that's the importance of vector. So now the idea is very clear that with vector, we can group related quantities into a single mathematical object. So here we have a weather information of a particular geographical coordinate. So rather than just specifying the temperature, we are making use of a vector which is holding the temperature, the humidity, and the wind. Now the weather is a single point in 3D space. So vector, so that is what the vector is. So now we can imagine or we can realize the evolution of mathematical thinking, like how we started with the numbers, the single isolated quantities, to vectors, which are group of related quantities, like grouping of related quantities into a single mathematical object. Then in this evolution, we have matrices or the grids. Now let us understand the concept of it. So collection of vectors is the matrices. So a matrix does not just show a state, rather it shows a transformation or an entire data set. So collection of vectors. So a vector is an information about a single point, but matrix can represent the entire region, wherein the column can be individual points. Or let us suppose if we talk about weekly weather. So what was the weather on Monday, Tuesday, Wednesday? So matrix can represent the entire information, the entire data set. And with matrix, we can see the relationship also, like how the trends, the temperature is changing with days. So that is what matrix. So matrix is basically collection of vectors. Now, if we talk about the power of matrix, like what advantage we get, if a vector is a snapshot, a matrix is a photo album or a map. So the idea is that vector you can treat it to be snapshots, and if we collect all that snapshots, the collection of all those snapshots will be a photo album, and that is what a matrix is. It allows us to perform linear transformations, such as rotating an image or projecting data from 3D down to 2D. Now, in this evolution of mathematical thinking, we have the step 5, that is the data science. So, data science is the massive systems. So, let us understand the concept first. So, using matrices so large that they efficiently describe reality. So, in data science, what we do is that we measure the entire systems. So we make use of massive matrices containing billions of rows and columns describing the reality. So in data science, we deal with massive matrices like huge data sets describing the reality. We process it to measure the entire systems. So data science is all about measuring the entire systems, measuring the reality, analyzing the massive systems. So we make use of massive matrices, massive data sets, huge data sets containing billions of rows and columns, which describes the reality. Now, what is the power of data science? Like what benefits we get? So data science is like linear algebra at scale. We stop looking at individual numbers and start looking at the topology, the shape of the data. If we talk about examples, so we have an interesting example of LLMs, large language models, for example, ChatGPT. So here, language as a matrix of word relationships. So large language models, they treat the entire human language as a matrix of word relationships. Similarly, if we talk about genomics, it represents the human genome as a matrix to identify disease markers. And if we talk about social physics, mapping every human connection on earth to predict economic trends. So when we talk about data science, we are talking about linear algebra at scale, wherein we are talking about huge data sets like large language model. It makes use of the entire human language. So we have a matrix which is representing the entire human language, the word relationships of the entire human language. So linear algebra at scale. And with this, we can measure the entire systems. We can analyze the entire systems. So now we can see the fundamental shift. Like we started our mathematical thinking by asking questions like what is the value, to asking question like what is a pattern. Because now in the modern world, mathematical thinking is not about measuring individual quantities. Rather, it is about measuring the entire system, analyzing the entire system. So now we are asking questions like what is the pattern rather than what is the value. And here linear algebra plays a very big role. Linear algebra, it allows, so linear algebra is the only branch of mathematics that allows us to compute these patterns across millions of variables at once. So using linear algebra, we can compute patterns across millions of variables at once, from equations to vectors to matrices to data. So if we talk about the progression from equations to vectors to matrices to data, this progression describes the transition from manual logic to automated intelligence. So we are talking about the transition from manual logic. So equations, they are valid only if the only for static systems. So equation is like a manual logic. So we are transitioning from manual logic to automated intelligence. See, as the number of variable grows, we stop focusing on the answer and start focusing on the system. So classical mathematics, it was all about identifying the single unknown or analyzing the single unknown. So in classical algebra, the focus is on isolation. You have one scale, one balance, and one missing weight. So in classical mathematics, in classical algebra, what we used to do is we used to solve, like we used to perform step by step arithmetic to isolate x and get the value of x. Now the scope is very limited. The scope is like small scale, human solvable problems. Like we can solve problems like if I have $10 and apple cost $2, how many apples can I buy? So such problems can be solved using classical algebra, using equations. Now the limitation is it cannot handle complexity. If you have 50 variables affecting a single outcome, writing 50 separate equations is inefficient and brittle. So, if we talk about the classical mathematics mindset, the idea, the philosophy is to find the value. But if we talk about linear algebra, in linear algebra, we are dealing with the interconnected systems. We are dealing with set of simultaneous equations. We are not just talking about one equation, we are talking about simultaneous equations. So linear algebra moves from one at a time to simultaneous logic. It recognizes that variables rarely act in isolation. They influence each other. So linear algebra is all about analyzing the simultaneous logic and interdependence between the variables. So if we talk about the workflow, so in linear algebra, you pack all your variables into a vector X and all their relationships into a matrix A. So we have a matrix and a vector. Vector is the variable and the matrix contains the relationship between those variables. So as you can see here, on the right side of the equation, we have a vector which is representing a variable, like set of variables, and on the left side we have a matrix which is the holding the relationship between the variables. So these numbers are like the weights or numerical measure of the relationship between the variables. So innovation, what is the innovation in linear algebra? So instead of solving for a single unknown x line by line, we use matrix inversion or decomposition, like the Gaussian elimination, to solve the entire system in one mathematical stroke. So we solve the entire system in one mathematical stroke. And what is the scope of linear algebra? It has a role to play in engineering, basic physics, economics. Like we can answer questions like how do these 10 ingredients interact to create this specific chemical yield? So when we are talking about how the variables are influencing each other, we are talking about linear algebra. In linear algebra, we are analyzing the interconnected systems. So in the transition from manual logic to automated intelligence, we have machine learning, which is the massive scale. So machine learning is essentially linear algebra at scale, or you can call it linear algebra on steroids. Like while a structural engineer might solve for 100 variables, an AI model like GPT-4 solves for trillions of parameters. So here we are talking about linear algebra on steroids, linear algebra at scale. We are not talking about 100 parameters. We are talking about trillions of parameters. So now let us try to understand the workflow of machine learning. So here you don't have a single result. Rather, you have a massive data set of bees. The goal is not just to solve the equation, but to find the best fit matrix A for the massive data set of bees. So once again, see, the idea is that we will consider this equation. Now B, we know that B represents the variables. So in machine learning, this B will be massive. We will be having a massive data set of variables, and this A is unknown. In machine learning problems, this A is not known to us. This A is unknown. So the idea is to find this A, find the relationship between the variables. That is what the machine learning problem is. So for machine learning is finding the best fit matrix A for the massive data sets of B's. Because this A is the relationship matrix. So machine learning is all about finding the relationship matrix for the massive data sets. Now, what innovation we have in machine learning? Optimization via gradient descent. So since the system is too large for a human to write the equations, we use optimization, we use gradient descent. So the computer guesses the weights in the matrix, checks the error, uses linear algebra to nudge those billions of numbers until the error disappears. So that is what the automated intelligence is. So system on its own, it will learn the relationship. The system on its own will learn the relationship. And that is what machine learning is. Machine learning is made up of two words, machine and learning. Here, machine is the computer, or you can call it algorithms. And learning means they will learn. What they will learn? They will learn the matrix, relationship matrix. They will learn the relationship matrix. They will learn the relationship between the variables. So algorithms will learn the relationship between the variables on their own. That is what the automated intelligence is. So they will make use of some mathematical techniques like optimization via gradient descent, where they will start with some guess, some random guess, and they will calculate the errors and fine tune the parameters to minimize the error. That is the core main idea of machine learning. Now, what is the scope of it? Scope of machine learning. So it is the modern magic. Like based on these billions of pixels, what is the probability that this is a picture of a cat? So with machine learning, we can very easily do image recognition, we can do classification, we can do some sort of forecasting, some sort of predictions. So that's the scope of machine learning. So we saw the shift in philosophy. Like initially, we were interested in finding the value in the classical algebra. But in the linear algebra, we started finding the intersection, the relationships. And in machine learning, the philosophy is to find the patterns, to find the relationship matrix, to find the patterns. So by moving from equation like 2x plus 3 is equals to 7 to an equation like ax is equals to b at scale, we have moved from calculating results to simulating intelligence. So in the modern world, the linear algebra is about simulating the intelligence, wherein we are dealing with equations like ax is equals to b, wherein b is a massive data set and a is a massive relationship matrix, which we are finding, which the machine learning algorithms, they are learning, they are finding using some sort of optimization techniques like the gradient descent. And that is what automated intelligence is about. That is what simulating intelligence is about. The central equation of linear algebra, ax is equals to b. So now we will discuss the central equation of linear algebra, ax is equals to b. So first, let us understand the meaning of ax is equals to b. What does this equation mean? So in linear algebra, ax is equals to b, if we talk about, it is not just a formula, it is a mathematical sentence. So depending on your goal, it can be read in two ways. It can be a system of constraints or a geometric movement. So in this equation, ax plus ax is equals to b. This A is the relationship matrix, or you can call it the rule. A is the rule. We'll discuss it in detail, what the rule means. X is the input, the knobs, and B is the result, the goal. Now, all these components we will discuss in some good detail. So, first, let us understand what do we mean by matrix A, which is representing the rule, the word. So, matrix A, it defines the environment or the physics of the problem. So, matrix A, it is representing the data, the transformation, and also the relationships. So if matrix A is representing data, then you can treat it as your library of information, like database of user movie ratings. So this matrix A, it can store data. It can even store transformations. If it is storing transformations, then it is acting as a machine that takes an input and moves, rotates, or stretches into a new position. Because if this matrix A, it is storing the transformations, then it will decide how to transform an input. And in this equation, X is the input. So this A, the values of the A, it will decide how to transform inputs present in the X, how to rotate, how to move, how to stretch it into a new position. Now the matrix A, it can also store relationships. So if it is storing relationships, then it is mapping how the inputs interact. So in a neural network, this relationship, we call it like the weight matrix, that determines how much importance to give to each piece of incoming information. So weight matrix is like how much importance to give to the inputs. So now it's very clear to us that if we talk about the matrix A, it defines the environment, the rule, the word. Now this matrix A, we can store either the data in it, either the transformations or the relationships. If we are storing it data in A, then it will act like a database of information or library of information. If we are storing transformations in matrix A, then it will act like a machine wherein it will decide how to transform inputs, because we multiply the input present in the X with A, and this A can also store relationships. Then we will call this A as relationship matrix. And in neural network, we call it the weight matrix, wherein this A holds the weight, which determines how much importance to give to each piece of incoming information. Now let us look at the vector X, the input, the knobs, what it is. So the vector X, it represents the specific configuration or the ingredients you are feeding into the system. So vector X is basically the specific configuration or the ingredients you are feeding into the system. So vector X, it can represent either the unknowns, the parameters, the features, the weights. If it is representing unknowns, like if the vector X is representing unknowns, so in classical algebra, X is what you are trying to find. Like how much of ingredient A and ingredient B do I need? So now it's very clear to us that if I talk about this X, it can represent an unknown which we are trying to find. Like how much of A should I use to get B, small b? This vector X, it can also represent parameters or the weights. So in machine learning, X represents the features of the data, like the height, weight, and age of a patient. So this vector x, it can represent features, it can represent weights or parameters. Like for a patient, it can be the height, weight, and age of a patient. This vector x, it can also represent the knobs. So you can think of x as a set of sliders. By changing the values in x, you change how much of each rule in matrix A is applied. So this is very interesting. So if A is containing some information or some rules or some transformations, then this x can act like a knob. Like let us suppose A is containing information, library of information. This A will act like a knob, like a filter. So by changing the values in this x, so vector x is acting like a knob, filter. By changing the values in x, you can change how much of each rule in matrix A is applied. So this is the importance of vector x. So now it's very clear that if I talk about vector x can represent specific configuration. It can act like a knob, or it can represent the unknowns, the ingredients you are feeding into the system. So we can represent unknowns. So x, vector x can represent unknowns. It can represent the features, the parameters, the weights, or it can represent the knobs. Now we can look at the vector b. So vector b is the result, the goal. So in simple terms, vector b is the outcome of the interaction between a and x. So when a and x will interact, the outcome is what the vector b is. So vector b, it can represent, like it represents the output of the interaction of a and x. It represents the target, the observations. So if the vector b is representing the output, then it is basically the final destination after the transformation. Like if A is a rotate 90-degree matrix and X is your starting point, B is where you land. So vector B can represent output, and if vector B is representing an output, it is representing the result of interaction between A and X. Similarly, vector B, it can represent target or observations. So in artificial intelligence, vector B is often the ground truth, the actual label. So in artificial intelligence, especially in supervised learning, we already have the target variable. Like for this input, this should be the output. So the known output, the known labels is what the vector B represents. So in AI, vector B can also be represented as targets or observations. So whatever the known labels we know, that is what the vector B is, the actual label, the ground truth. And vector B can also be the solution. So vector B can also represent the solution. So the idea is that we often know the matrix A, our data, and vector B, our desired outcome. And we use linear algebra to work backward to find the perfect X that makes the equation true. So this vector B can be the solution. So we know the solution, we know the matrix A, and using linear algebra, we will calculate the X, because we know that vector X can be an unknown. It can represent unknown. So now it's very clear to us that if I talk about vector B, that vector B can be uh, an output, like vector B can represent output. So output means it's the outcome of the interaction between A and X. When A and X will interact, the result is what the vector B is representing. The vector B can represent target or observations. The ground truth in artificial intelligence, the ground truth, the actual label is what can be represented as vector b, and vector b can also represent the solution. So using this and the matrix A, we can find the unknown vector x. If we put it all together, the three perspectives, so if the perspective is solving, then x is unknown. So if the perspective is solving, then what exactly we are doing is, given the matrix A, what what input x should be given to get the result b. So that is what solving means. Solving means solving for the unknown x. That can be one perspective. The other perspective of using this equation can be transforming. So in transforming, what we do is that b is unknown. In transforming, b is unknown. So the idea is very clear that, okay, we apply some set of transformations. The rules is represented by the matrix A. So if I apply these rules, which is given by the matrix A, to this input x, where do I end up? So that is what transformation is. So we can make use of this equation for transforming, for solving, and for learning. So in learning, A is unknown. So in learning, what we are asking is, given these inputs x and these results p, the ground truth, what are the underlying rules A? So in learning, we are trying to find the relationship matrix. Like if this is the input, this is the output, how input and output are related to each other. So the matrix A will be treated as a relationship matrix. Matrix A will represent the relationship matrix or the weight matrix. So now it's very clear to us that the equation Ax is equals to B. Now it's very clear in linear algebra, Ax is equals to B is the central equation. We can use this equation from the perspective of solving, where x is unknown, from the perspective of transforming, where b is unknown, and from the perspective of learning, where a is unknown. Now let us look at the geometric interpretation of the equation Ax is equals to b, the geometric interpretation. So let us look at Ax is equals to b as transformation. So in the geometric view, we stop thinking about solving equations and start thinking about moving through space. So we stop solving equations and start thinking about moving through spaces. So the idea is that, let us suppose we are starting with some original space, we are applying some transformation, and because of that, we will get a new space, a transformed space. So that is what Ax is equals to b as transformation is. So A contains the transformation rules, x is the input. So if we apply the transformation rules on the input, we get a transformed space, and that is what the B is. So here x is the input, A is the transformation rule, and B is the output, the transformed space we got. So the vector x, which is the input, it starts at one location, and the matrix A, which contains the rules, transformation rules, it acts as a force that moves the vector x into a new location, vector b. So vector matrix A is acting like a force which will transform the input vector x into a new vector b, into a new space. So here matrix A is the space wrap. So matrix A acts on x to move it to b. Now we will discuss the concept of linearity and basis in this transformation. So if I talk about linearity, the idea is that uh, after applying the transformation also, the concept of linearity states that the origin always stays fixed and all parallel lines remain parallel after the movement. So that is what linearity is. So linear transformation. So linear transformations are those where origin will not get shifted and all the parallel lines after transformation, they will stay parallel. So that is the linearity in transformations. And what is basis? So matrix A essentially tells the computer where the standard directions like up and right should land in the new space. So bases are like the standard directions which helps in transforming the input X into a new space B. And matrix A, it contains the transformation rules. Matrix A contains the rules which tell where the standard direction should land in the new space. And these standard directions are the basis. Now we will look at the four key moments. The four key moments, like the four major transformations that we can do. The first one is the rotation. So the matrix spins the vector around the origin without changing its length. So in rotation transformation, we don't change the length, rather we just spin it through some angle. So the matrix A, it spins the input vector without changing its length. So in artificial intelligence, rotation is used in computer vision to recognize objects regardless of their orientation. So the idea is that if we have a cat which is tilted 45 degrees, then uh, computer vision makes use of a rotation matrix to rotate it to the normal angle and then process it. So that's the application of rotation transformation in computer vision. Like let us suppose I have a cat which is rotated 45 degree. So we will make use of this rotation transformation to bring it back to the normal angle and process it further. So in rotation, we the transformation matrix, it just spins the input vector without changing the length. Then the next transformation is the scaling. The next transformation is the scaling. So in scaling, the transformation matrix, it stretches or shrinks the input vector along certain axes. So scaling means either stretching or shrinking the input vector along certain axes. So that's the idea of scaling. So the transformation matrix A, it stretches or shrinks the input vector along certain axes. So in data, this scaling is normalization. If one feature has huge numbers and another has small numbers, like salary can be big, age can be 2-digit number, salary can be 5-digit, 6-digit, 7-digit. So we use a scaling matrix to put them onto the same playing field so the AI does not get biased towards the large numbers. So that technique is the normalization. And normalization makes use of scaling. Then the next transformation which we have is the projection. So projection is like casting a shadow. Projection is like casting a shadow. So it takes a high dimensional vector and flattens it onto a low dimensional surface, like from 3D to 2D. That is what projection is. So in projection, the transformation matrix, it takes a high dimensional input vector and transforms it into a low dimensional space, like from 3D to 2D space. That is what projection is. In graphics, this is how a 3D video game world is displayed on your flat 2D monitor. And in data science, it is how we take 1000 different data points about a person and project them onto a single risk score. So that is what projection transformation is. Then the next transformation is the compression. That is a shearing and squashing. So here the transformation matrix, it collapses the space. So compression means collapsing the space. So if the matrix is singular, singular matrix means determinant is zero. If the determinant of the matrix is zero, then it's a singular matrix. Then it squashes the entire space into a flat line or a single point. So in compression, the transformation matrix, it will compress the space of the input vector. It will squash the input vector either into a flat line or a single point. In artificial intelligence, this is the core of autoencoders. So we take a high definition image and squash it into a tiny vector that captures only the most essential information, and then we try to reconstruct it later. So squashing is what compression is. So now it's very clear that four transformations we can perform: the rotation, the scaling, the projection, the compression. Each has got its own significance. They have a role to play in AI as well. Now let us look at why this matters for AI. See, when a deep learning model thinks, it is actually passing your input through a sequence of these transformations. So deep learning is basically a sequence of transformations. So in layer 1, the deep learning in the layer 1, it might be rotating the input vector to find edges. In layer 2, it might be scaling the input vectors to find shapes. So in layer 2, it might be scaling the edges to find shapes. And in layer 3, it might be projecting the shapes into a category like a face, a background. And linear algebra is the study of these geometric actions in the AI's brain. So now it's very clear that geometric transformations do have a role in AI. So linear algebra is the study of these geometric actions. By understanding the transformation matrix, we know exactly how the data is being reshaped as it moves through the brain of the AI. Now we will discuss why this matters for machine learning, like why the central equation of linear algebra AX is equals to B matters for machine learning, or what is the significance of the equation AX is equals to B in machine learning. So machine learning is mostly matrix operations. In machine learning, we will be coming across lots of matrix operations. So at its core, machine learning is finding a mathematical function that maps inputs to outputs. So in machine learning, we know the input, we know the output, but we don't know the mathematical function. So machine learning at its core is the process of finding a mathematical function that maps inputs to outputs. So we know inputs in machine learning, we know the outputs, and we determine the unknown function. Because we deal with thousands of inputs simultaneously, linear algebra is the only way to perform this mapping efficiently. So now let us see how most famous ML algorithms are actually just specific matrix operations. So if we talk about linear regression, so linear regression is basically AX is approximately equal to B. So in linear regression, we are predicting a continuous value like a house price based on the input features. So we are predicting a continuous value based on the input features. So in linear regression, this central equation of linear algebra AX is equals to B, if we consider, so the matrix A, so here is the representing the historical data. So in linear regression, this matrix A is the historical data matrix. Vector B is the actual prices, the ground reality, the ground truth. And vector X is the weight or importance of each feature. So in linear regression, A is the historical data matrix, B, vector B is the actual price vector, the ground reality, and vector X is the weights vector. So in the real world, a perfect solution usually does not exist because the data is noisy. So in linear regression, we are searching for X. So we are solving this equation to find the unknown X, because B we know, capital A we know, X we are solving, we are finding it. And why we are writing using approximate and not equal? Because in the real world the data is noisy. We use normal equation or least squares to find the best x. So now it's very clear that linear regression makes use of this equation ax is equals to b. Similarly, neural networks, they make use of a equation y is equals to wx plus b, which is a form of the central equation ax is equals to b. Now let us understand the concept in neural networks. So in neural networks, this is the fundamental layer of almost every AI, from ChatGPT to Tesla's autopilot. So let us understand this equation, the matrix view. So here in neural networks, the small x, the x vector, it is the input. So here x is the input. It's the input vector. Capital W is the weight matrix. And this weight matrix will be holding the weights. And small b is the bias vector. So bias vector, it's an offset. X is the input and W is the weight matrix. So in neural network, we do the matrix vector multiplication operation. So when you run a large model, your GPU is doing matrix vector multiplication billions of times per second. So it is just multiplying the matrix, which is the weight matrix, with the input vector, adding it with the bias vector to get an output. It is comparing that output with the ground reality. The difference is the error, and based on the error, it is updating the weights. It is updating the values in the weight matrix. Once again, multiplying it with the input feature, input vector, adding the bias, and updating, getting the output, calculating the error, and updating the weights. It will keep on doing it until the error is minimized. So neural network also makes use of the equation wx plus b. Even the principal component analysis, it makes use of the matrix operations. So the idea of principal component analysis is like reduce massive data set, for example, of 100 features to essential 3 features without losing information. So that's the concept of principal component analysis. So in principal component analysis, we reduce the massive data sets containing hundreds of features to essential data sets with just 3 features without losing information. Now let us understand the matrix view. Principal component analysis, it calculates the covariance matrix of your data. So whatever data you have, the data set, we calculate the covariance matrix and then find the eigenvectors and eigenvalues of the covariance matrix. Now eigenvector, it points in the direction of the most spread. Eigenvector points in the direction of the most spread, the variance. So in your data, by keeping only the vectors with largest eigenvalues, you effectively compress the reality of the data into its most essential parts. So keeping the largest eigenvalues, you can eliminate other eigenvalues. So you can just compress the reality. You can get rid of unnecessary features, and you can transform hundreds of features into essential 3 or 4 features without losing information. And that is what principal component analysis is all about. So in principal component analysis, we convert our massive data set into a covariance matrix, and we get the eigenvectors and eigenvalues of those covariance matrix, and we make use of those eigenvalues and eigenvectors to reduce the massive data set into fewer data sets, fewer features without losing information. Now these recommendation systems, it also makes use of the matrix operations. So recommendation systems, they make use of matrix factorization. So the concept of recommendation system is very simple. Like the idea is predicting what you want to buy before you know you want it. So recommendation system will recommend you that you should buy this. Now the matrix view, let us understand. So imagine a giant grid where every row is a user and every column is an item. So we have a user item matrix. So in the user item matrix, every row is the user, every column is the item, and the numbers are the preferences. And it is like a sparse matrix. Most of the cells are empty. Now what we do here is we take this giant user item matrix, I'm calling it R, and we are breaking it into two smaller skinny matrices U and V, such that U times V is approximately R. Now this process of decomposing a user item matrix into two smaller U and V matrix reveals hidden features, like user 1 likes action movies and movie X is an action movie, allowing the AI to fill in the empty cells with high accuracy guesses. So we do the matrix factorization. So in recommendation systems, we do the matrix factorization. So we start with a user item matrix and we break it into two small matrices U and V, such that U times V is approximately the user item matrix R. And this U and V matrix, they reveal the hidden features, which helps the AI to recommend to the users. So now it is very clear to us that machine learning is mostly matrix operations. Regardless of what algorithm you are using, any famous machine learning algorithm you take, you are doing some sort of matrix operations. And now one very interesting discussion we will do. Now this matrix operation has a very interesting hardware connection, especially with the GPU. See, the reason we use matrices in machine learning algorithm is not just because the math is elegant, but because of the efficiency. So the idea is, if we use CPU, central processing unit, so CPU is like scalar operations one by one. But with GPUs, graphical processing units, they are designed to process entire rows and columns at once. So we can perform simultaneous or the parallel matrix operations. We can perform billions of operations simultaneously. And there matrix comes into the picture. So if we use matrix, we can efficiently utilize the computing power of GPUs. With GPUs, we can perform billions of operations, matrix operations simultaneously. So the reason for using matrices in machine learning is efficiency. So without linear algebra, AI would be millions of times slower, because we know that AI, it is compute intensive. So without linear algebra, the operations would be very slow. AI would be millions of times slower. Linear algebra makes real-time translation, image generation possible. Now let us look at the significance of AX is equals to B. Significance of the equation AX is equals to B. So the equation AX is equals to B is the master equation of modern computing. So while this equation looks a simple algebraic statement, it serves as the universal interface between human logic and machine execution. So this equation AX is equals to B, it serves as the universal interface between the human logic and the machine execution. Now let us understand the significance of this equation in certain critical domains. So in linear systems, this equation is the core of linear systems. So this equation is the most direct application in linear systems. Any problem where you have multiple constraints and multiple variables can be written in the form of AX is equals to B. Now the significance is, this equation allows us to solve for hundreds of variables at once. because in this equation, this x is not just one variable, but it is a vector. X is a vector, b is a vector, and a is a matrix. So we can solve for hundreds of variables at once using this equation, like balancing a chemical equation or calculating the load bearing capacity of a bridge. It uses algorithmic methods like Gaussian elimination. So linear systems, they make use of algorithmic methods like Gaussian elimination. The core of linear system is this equation, Ax is equals to b. In neural networks and deep learning, this equation, the master equation, acts the engine, acts like the core engine. Ax is equals to b. So in a neural network, every thought is a matrix vector product. So in neural networks, X is the input, like for image, it can be pixels. A is the weight matrix, the knowledge which it is learning, and B is the bias, the next layer activation. So here B is not the bias, sorry, B is the next layer activation. Like when I multiply the input with the weight matrix, the output I'm getting, that is the B, and B I will send it to the next layer. So B is the next layer activation here in this equation. So Ax is equals to B is the engine of the neural network. X is the input, A is the weight matrix, the knowledge, and B is the next layer activation. Now in deep learning, in a deep network, is a simple chain of Ax is equals to B. So initially we are starting with A1x, the result, we're multiplying it with A2, then A3, and every time this A we are updating. So it's a stacking operation. So linear algebra allows us to stack these operations to create complex artificial intelligence. So with linear algebra, we can create complex AI. Now, this master equation Ax is equals to B, it also has a role to play in optimization. In optimization, this master equation, it provides a direction. Now see, optimization is the process of finding the best version of something. Like optimization is like minimizing the loss, maximizing the profit. And AI optimization is minimizing the loss. So basically, in AI, for optimization, we calculate the Hessian and the Jacobian, which are just the matrices of derivatives as A. So in optimization, the capital A is the matrices of derivatives. So capital A is the Jacobian matrix or the Hessian matrix. Now, it is used to find the direction to move to optimize the parameters. In regression and least squares, the central equation Ax is equals to B, it helps us in giving the best fit. So in the real world, Ax is equals to B usually has no perfect solution because the data is messy and noisy. So no perfect solution we can expect. Rather, we will be going for the best fit. So least squares is a technique to find X, making Ax closest to B. So least square is a method of determining the unknown X. When we multiply it with A, we get not exactly equal to B, but close to B. Similarly, in regression, this is the math behind trend lines. In regression, we are predicting a continuous value, like we are predicting stock prices or housing trends. And in regression, we make use of a normal equation. A transpose into A into X is equals to A transpose B. So what we are doing with the central equation, the master equation Ax is equals to B, both the sides we are multiplying it with the A transpose A transpose. So we are calling it the normal equation and we make use of it to minimize the distance. So now it's very clear that the master equation Ax is equals to B, it has a role to play in least squares and also in the linear regression. Now the central equation Ax is equals to B, it also plays a role in scientific computing wherein it helps in simulation. So modern science, it runs on simulations. Like we simulate the weather patterns. We do simulations in fluid dynamics, nuclear physics. So simulation problems are usually defined by differential equations. Computers cannot solve differential equations directly. So they have to discretize differential equations into millions of tiny linear pieces. So computers, they discretize differential equations into millions of tiny linear pieces. So basically, we turn a complex physics problem into a massive Ax is equals to B problem. So the tiny linear pieces are Ax is equals to B. So in solving differential equations, we like the computation, the computing, the algorithms, they convert or they discretize the differential equation into millions of tiny linear pieces. Ax is equals to B. So we are turning a complex physical problem into a massive Ax is equals to B problem that supercomputers can crunch. So that's the idea. So in scientific computing also, this master equation Ax is equals to B has a role to play. Now it is very clear to us why Ax is equals to B is the central equation of the linear algebra. Why it is called the master equation of modern computing? Because this equation has a role to play in linear systems, in neural networks, deep learning, optimization, regression, least squares, scientific computing. So in this equation, why this equation is so powerful? The secret is the linearity. Why the central equation is so powerful? The secret is the linearity. The reason Ax is equals to B is the foundation for everything is that non-linear problems are incredibly hard for computers to solve directly. So the strategy is, so the non-linear problem are hard to solve. So what we do is the strategy, we take a curved, messy, non-linear word and zoom in until it looks flat, linear. So the strategy is to zoom in on curved or messy word until it looks flat, linear. And by treating everything as linear systems, we can use the most optimized code ever written for speed, for efficiency, to solve problems at the speed of light. So the linearity is the key. So the idea is very clear that any non-linear problem is hard. We have to convert it, we have to transform it into a linear problem. And with linear problem, we can make use of the GPU, wherein we can carry out billions of computations simultaneously. So the bottom line is, if you can express a problem as a Ax is equals to B, you have a path to a solution. So the idea is that we just have to convert or express a problem as Ax is equals to B problem. And if we are able to do that, then we have a path to a solution. And if we are not able to do that, then we are stuck in the dark. Applications of linear algebra in machine learning, optimization, compression. Now we will discuss applications of linear algebra in machine learning, optimization, and compression. So neural networks depend on linear algebra. Now every layer in a neural network is matrix multiplication. So in a neural network, thinking is essentially a high speed relay race of matrix operations. Every time an AI processes a prompt or identifies an object, it is performing a massive chain of linear algebra. So every layer of a neural network makes use of an equation called y is equals to wx plus b, which involves matrix multiplication. Now let us decode this equation y is equals to wx plus b. So this single equation y is equals to wx plus b is the fundamental neuron logic used by everything from simple predictors to GPT-4. So in this equation, the W is the weight matrix. The W is the weight matrix. The weight matrix is the model's knowledge. The weight matrix represents the model's knowledge. So the idea is this weight matrix is basically a grid of numbers. It's a matrix, it's a grid of numbers representing the connection strengths. Now, this weight matrix is the one which the AI learns. So this weight matrix, it represents the AI's learned patterns. It is representing the model's knowledge which the AI has learned. So this is what the AI actually learns during training. If the AI is trying to recognize a circle, the numbers in W will be high for circular patterns and low for straight lines. So the numbers in this weight matrix, it is representing the connection strengths. It is representing a pattern which the neural network is trying to learn, which the AI is trying to learn. So when we multiply the weight matrix with inputs, if we multiply the weight matrix with the input vector, that is the x, you are essentially asking how well does this input match the patterns I have learned. So matrix multiplication of W with the vector x is basically equivalent to asking a question, how well does this match learned patterns? The idea is that the result of the multiplication of the weight matrix with the input vector, we compare it with the ground reality. And if it is close to the ground reality, it means the model's knowledge is appropriate. The model's knowledge is accurate. And if the multiplication of W with X is far away, if the difference between the predicted value and the actual value is large, it means the model's knowledge is not up to the mark. There is a need for more training. There is a need for more training. So that is the significance of the weight matrix W. So the result of the matrix multiplication of W with the input vector X will determine the accuracy of the model's knowledge. Now in this equation, we have small x, which is the weight, which is basically the input vector. So x is the input vector. It is the signal. So the incoming data, that incoming data can be raw pixels, word embeddings. So the incoming data into the layer. So in the first layer, this is the raw data. That can be pixels, audio frequencies, or word embeddings. In the later layers, it is the abstract features detected by the previous layers. Now, what is the role of this input vector? It provides the current state that needs to be processed. Now, in this linear equation, we have small b, which is the bias vector. So, small b, the bias vector, it is the threshold. So, bias vector is basically a list of numbers which are added after the multiplication. So the idea is that when we multiply the weight matrix with the input vector x, we add bias vector also. We add the values of the bias vector. So bias vector contains list of numbers that are added after the matrix multiplication. Bias allows the network to shift the activation function. So bias, it allows the network to shift the activation function. Even if the input Wx is 0, the bias ensures the neuron can still fire if necessary. So the idea is that if the product of Wx is 0, because of bias, the result will be some valid number, some positive number or some negative number. So this bias, it ensures neuron can fire even if Wx is 0. Bias provides the flexibility needed to fit complex data. So in this equation, y is equals to wx plus b. B is the bias vector, list of numbers which are added to the result of the multiplication of W with the X, the bias vector, it ensures neuron can fire something even if the product Wx is 0. And bias, it provides flexibility needed to fit complex data. Then we have small y, which is the output vector. So small y is the output vector, which is the inside. So this is basically the result of the transformation. The result of the transformation, y. It becomes the input for the next layer. So the y becomes the input for the next layer. So now it's very clear to us that in a neural network, for every layer, like in every layer of a neural network, we will perform the operation y is equals to wx plus b. Now deep learning is basically a chain of transformations. Deep learning is basically a chain of transformations. So deep learning is called deep because it stacks many of these layers on top of each other. Mathematically, the deep learning, it looks something like this. So mathematically, the deep learning, it looks like y is equals to activation. So to make things easy, we start with the first, like w1x plus b1. So in the first layer, we will calculate w1x plus b1. The result, we are passing it in an activation function, and that result, we are multiplying it with the w2 plus the b2, because we know that the result of the first layer will be the input for the second layer. So the result of the first layer, we are multiplying it with the w2 and adding the b2 to it and passing it through an activation function, which will become the result of the second layer, which will become the input for the third layer, which we are multiplying it with the w3, adding it with b3 and passing it through the activation function and get the result. And if all the layers have been covered, then we will get the final input. So that is what a chain of transformation is. So in a deep learning, we have n layers. So in the first layer, we will be calculating the activation of wx plus b. The result will be the input for the second layer. There once again, using this input, we will calculate w2 into this input plus b2 and passing through the activation function to get the result, which will be the input for the third layer. And like that, we will keep on doing until we get the final output. So that is what the deep learning is, a chain of transformations. Now in a deep learning, each layer takes the space defined by the data and wraps it. So in deep learning, actually in every layer, it is taking some data and applying some transformation to it. So the idea is that in deep learning, so this is the input. I call it the input vector. So in the first layer, I am directly passing the input vector, and the first layer will perform some transformations to it. The first layer might perform a rotation to find edges. And now whatever edges it found, it will pass it to the second layer, which will further perform some transformations to it. Let us suppose the second layer might perform scaling to identify shapes like the eyes, nose, wheels. Then we will pass that to the next layer, those shapes. Now the final layer might perform some sort of projections to squash all complex geometry into a single probability value. And the answer of the final layer is a number which is basically a probability, like 99% chance that the input is representing a cat. So this is how the deep learning works, layer by layer operation. And in every layer, we are using the same formula, y is equals to wx plus b. Now let us look at the computational reality. So in deep learning, because every layer is just a matrix operation, wx plus b, the entire field of AI hardware, like the NVIDIA GPUs and Google TPUs, is built specifically to do fused multiply add operations. So the AI hardware, the chips, they are built to perform fuse, multiply, add operations. We call it FMA operations because we know that in deep learning, in every layer, we just have to compute this operation. We have to perform a matrix multiplication along with the addition. So fused, multiply, add operations. So these chips don't think in logic. They are massive engines designed to multiply and add matrices at the speed of electricity. So because of this linear algebra, because of this matrix computations, we can perform large scale operations in lightning speed. So that's the main idea. So the AI hardware, the GPUs by the NVIDIA, the TPUs by the Google, they these AI hardware are built for FMA operations, fused multiply add operations. So these hardware, they don't think in logic, but they just multiply and add matrices at the speed of electricity. So that is the computational reality. So now we will look at the applications of linear algebra in optimization. So optimization and linear algebra. So see, basically AI, it learns by optimization. The goal of AI is to optimize, that is minimize the loss function. Now let us see what role do linear algebra plays in optimization. Let us try to understand that. So training an AI model isn't a guess game. It is a high precision search through a multi-dimensional landscape. So basically in artificial intelligence, when we are training a model, we are finding the most optimal values for the parameters. If we fit those values, we will be able to minimize the loss. So training an AI model means a high precision search through a multi-dimensional landscape. And optimization is the process of the minimum, finding the lowest point, the minimum error in that landscape. And linear algebra provides the compass and the map. So linear algebra provides the tools needed to find the lowest point in that landscape. So training an AI model is basically a high precision search through a multi-dimensional landscape. Optimization is the process of finding the lowest point in that landscape. And linear algebra provides the compass, the map, the tools to find the lowest point. So that is the significance of linear algebra. So linear algebra provides us the tools through which we can perform optimization. Now let us look at AI training as math problem. Now let us look at AI training as a math problem. So when we train a AI model, we are trying to find the perfect values for the weight matrix. So training an AI model means finding the unknown weight matrix. The objective is to minimize the loss function. When we minimize the loss function, our prediction will be very close to the ground reality. Loss function is basically the mathematical difference between what the AI predicted and the ground truth. The mathematical difference between the prediction and the ground truth is the loss function. And our goal is to minimize the loss function. That is the objective. The scale. Now, basically, to minimize the loss function, we will be optimizing billions of parameters simultaneously. So when we are training AI model, we will be optimizing billions of parameters simultaneously. And to do it, we cannot do it by hand. You will need a system of vectors to move the model towards accuracy. So we will be needing a system of vectors to move towards accuracy. So now it is very clear to us that training an AI model is like a high precision search through a multi-dimensional landscape. Optimization is the process of finding the lowest point in that landscape, and linear algebra provides the compass, the map, the tool to find the lowest point. Mathematically, training an AI model means finding the weight matrix, finding the perfect values for the weight matrix, which can minimize the loss function. So if we have found a perfect weight matrix, if we multiply it with the input vector, so whatever predictions we got, it will be very close to the real values, the ground values, the actual values. So that is the objective of training an AI model. The objective is to minimize the loss function. And thus, if we talk about the scale, when we are training an AI model, we are optimizing billions of parameters simultaneously. And to do that, we will be needing a system of vectors which will be moving towards accuracy. That is the idea. Now let us understand the tools the linear algebra provides to help us in optimization. So the linear algebra, it provides us the gradients. So the gradients are like compass. They show the direction. They show that in which direction should we move and how much we should move. So linear algebra provides gradients as tools. So the gradient is basically a vector of partial derivatives. In linear algebra terms, it points in the direction of the steepest slope of the error. So in terms of linear algebra, gradient, you can consider it to be a vector which is pointing to the steepest uphill slope. So the idea is that you are at a point. Now, in this from this point, in different directions, you might have different vectors with different steepness. So gradient is a vector which is pointing to the steepest uphill slope. Like let us suppose this one. So if this is the steepest uphill slope, then this will be the gradient. Then I will be taking this direction. So gradient is a vector of partial derivatives which is pointing to the steepest uphill slope. Now to improve or to optimize the AI, it takes the negative gradient to move downhill because our goal is to minimize the loss. So the steepest uphill slope, we will move in a direction opposite to it. So we take the negative gradient to move downhill, and that is what the gradient descent is. Gradient descent means descending, moving down, the moving downhill in the direction of the gradient or opposite to the direction of the gradient. Now, without vectors, without this gradient, we could not calculate how 100 million weights interact to affect a single result. Because of this mathematical tool, because of this gradient, which is a vector of partial derivatives pointing to the steepest uphill slope, we can very easily find the direction in which we should move. So we take the negative gradient to move downhill, the gradient descent, and we get a direction which will take us to the lowest point in the landscape, which will minimize the error. So gradient is a very powerful tool which plays a role in optimization. Hessians, the curvature. So if the gradient tells you the direction, the Hessian tells you how fast the terrain is changing. Hessian is giving us the information about the curvature, how fast the terrain is changing. So gradient gives us the direction. Hessian tells us the speed of terrain change. So Hessian is a square matrix of second order partial derivatives. So Hessian is also a matrix, like Hessian is a matrix. It's a square matrix of second order partial derivatives. So Hessian matrix helps the optimizer understand if it is in a wide flat valley where it can take big steps. So Bayesian information, like Bayesian matrix will give us an information whether we are stuck in a wide flat valley wherein the speed of terrain change will be very less, or we are in a narrow steep canyon where we have to take the careful steps because the speed of terrain change is extremely high, the curvature we can see. And because of this Bayesians, we can determine when to take big steps and when to take small steps. Because gradient is telling us the direction, and we know that, okay, we know that we have to move in this direction. But if we take big steps, we might miss the lowest point. We might miss the minima. We can overshoot it. That might happen. So Bayesian will give us an idea. The curvature will give us an idea that how big steps should we take. If the speed of terrain change is very less, then we can take big steps. But once we are getting higher values of Bayesian, the speed of terrain change is high, then we have to take small steps. Careful steps we have to take. So this Bayesian is the basis for advanced second order optimization algorithms. Now the next tool of linear algebra which plays a role in optimization is the least squares. So least squares is the shortcut. So the idea is that sometimes we don't need to search for the best answer. We can calculate it directly. And let us see how we can calculate the best answer directly. Rather than searching for the best answer, we can calculate it directly. So in linear regression, the least squares method finds the point where the error vector is perpendicular or orthogonal to the data space. So in regression, we use the concept of projection. Projection means finding the points where the error vector is perpendicular to the data space. So now let us suppose this line is representing the data space and this is the point. Now the distance of this red point from the blue line is the error, and the error vector is this, and the perpendicular of this point is this. Let me draw it with a green pen or orange pen to make it visible. So this is the idea. So in regression, if we just solve this equation, A transpose AX is equals to A transpose B, the linear algebra will find the single best fit in one shot. So no need to do any gradient descent or search. Just solve this equation to get the single best fit. So that is the least squares method. So in least squares, it's a tool of linear algebra. Using it, we can calculate the best answer rather than finding for it. So we just have to solve this linear algebra equation A transpose AX is equals to A transpose B to get the single best answer. So the next important tool of linear algebra which plays a role in optimization is the projections. So projections means simplifying the search. So high dimensional optimization is low. So high dimensional optimization means we are having various features, high dimensional space, like lots of features we have. Now optimization will be slow. If we have lots of features, the optimization will be slow. So in high dimensional spaces, the optimization is slow. So high dimensional optimization is slow. Projections allows us to simplify the problem. And let us see how. So the idea is that by projecting a complex high dimensional error surface onto a low dimensional subspace. So if we can transform a high dimensional error surface to a low dimensional subspace, if we can reduce the dimensions, we can find a good enough solution much faster. And this is what we do in stochastic gradient descent. So this is vital for stochastic gradient descent, which looks at small batches of data at a time. So rather than exploring the entire data set, we are just exploring small batches of data. So that is what stochastic gradient descent. So the idea is very clear that using the concept of projections, we can simplify the search. Idea is that if we project a complex high dimensional error surface onto a low dimensional subspace, we can simplify the search. We can perform the search much faster. So we saw the tools linear algebra provides for optimization, like the gradients, the Hessians, the least squares, and the projections. Now let us discuss the chain rule and back propagation. Now one very interesting question we have, like how does the output mistake tell a neuron at the input to change? So the idea is that, see, in a neural network, what we do, we start with some random weights, and using those random weights, we perform some matrix operations in every layer. In every layer, we will calculate y is equals to wx plus b. And in this way, at the final layer, we will get the output. And we match or we compare that output with the ground reality, the actual result. And the difference is the loss. Now, let us suppose our output was a very big mistake. It is very far away from the actual value. It means our neural network made a mistake. It means whatever the initial guesswork we did, whatever weights we guessed, they were wrong. Now, a very big question is how we will update the weights so that we can minimize the loss. How we can update the weights so that in the next turn, our output will be closer to the actual output or the ground reality. So that is the idea. So that is what the chain rule and the back propagation is. So what we do is we go for matrix transpose. So what we do is that whatever the error we got, the difference between the predicted value and the actual ground reality, we will send it backward. So during the training, the error is sent backward through the network. This involves multiplying the error vector by the transpose of the weight matrix. So that is what the back propagation is. So whatever the error was, we will send the error backward through the network, and in every layer we are multiplying the error vector by the transpose of the weight matrices. If we talk about linear flow, so linear algebra allows the blame for an error to flow perfectly across millions of connections, ensuring every single parameter is adjusted by exactly the right amount. Because of this back propagation, the linear algebra is allowing the blame for an error, like the whatever the error is, it is propagating from the backward direction. It is flowing perfectly across millions of connections, ensuring every single parameter is adjusted by exactly the right amount. So that's the idea of back propagation. So now in this way, the weights they get updated, the parameters they get updated, because whatever the error we got, we send it from the backward direction to all the connections. And in this way, the weights of the connections they get adjusted. And then we do the forward pass. In the next forward pass, the output will be close to the actual output, the ground reality. And once again, whatever error we got, we will back propagate it to update the weights. And we keep doing it until our predicted value is very close to the real value. And this is how a neural network or a deep learning it works. So basically, in a neural network, we have the learning loop. So there is a forward pass wherein we start with some random weights. In every layer, we calculate wx plus b. The output is sent to the next layer. Like that, we perform operations and we get the final prediction. Then we will calculate the error. We will compare the output vector with the target vector, which is the ground reality vector, the actual vector. And the difference is the error. We calculate the error and then we optimize it. To optimize it, we use gradients, which are vectors, which will tell us the direction, in which direction should we move. And we have Hessians, which will give us the idea about the curvature, like how big the step should be to update the weights. So gradient will tell us whether we should increase the weight or decrease the weight, and Hessian will tell us the amount, whether the update should be a big update or a small update. And once we optimize it, and for optimization, we make use of the back propagation. So the error vector, we propagate it from the backward direction and we update all the weights. And once the weights are updated, we once again go for a forward pass. Now we have a updated weight matrix. So when we go for a forward pass, the final prediction will be a bit different and it will be bit closer to the target, to the actual input, the actual value. And once again, we'll calculate the error, optimize it, and we will keep on repeating it billions of times until the error is close to zero. And this is how the learning loop, this is what the learning loop is. Now let us discuss the application of linear algebra in data compression. So data compression and linear algebra. So what role does linear algebra plays in data compression? So first let us understand the meaning of data compression. Like what do we mean by compressing information? So data compression is the art of finding the essential part of a matrix and throwing the rest away. So data compression is basically the art of finding the essential part of a matrix and throwing the rest away. Now, in linear algebra, this technique or this process is called low rank approximation. And it's how we move massive amounts of data across the internet without breaking it. So what we do is that we compress the data and then we send it to the network. So low rank approximation is how we move massive amounts of data across the internet without breaking it. So data compression is very clear. Data compression is the art of finding the essential part of a matrix, throwing the rest away. And we make use of a technique of linear algebra called low rank approximation to do it. Now, if we talk about the master tool for data compression, so singular value decomposition, SVD. So singular value decomposition is the master tool. So you can call it like single value decomposition as the Swiss Army knife of data science. So SVD, it takes any matrix A and breaks it into three specific parts. So that is what the singular value decomposition. So we break a matrix into three parts: U, sigma, V transpose. So here U and V are the directions of pattern in your data. So this U and V matrices, they tell you the directions of the patterns in your data. And sigma, it is a diagonal matrix of singular values. And these singular values are ranked from largest to smallest, representing the importance of each pattern. So in a singular value decomposition, we decompose any matrix A into three components or three parts: U, sigma, V transpose. U and V represents the directions of patterns in your data, and sigma is basically a diagonal matrix of singular values which are ranked from largest to smallest, representing the importance of each pattern. Now, how exactly we compress the data? Like how SVD compresses the data? So to compress, data, you simply truncate the matrix. Like you keep only the top few singular values and discard the tiny ones. And with this, we are capturing 90% of the information using only 5% of the storage. So now the idea is very clear, like how we do data compression. We make use of a technique of linear algebra, that is the singular value decomposition, wherein the matrix containing the data, we break it into three parts, and the sigma is a diagonal matrix of singular values which are ranked in largest to smallest. So the only the top few singular values we will consider, and all other values we can truncate, we can discard it. In this way, we are retaining 90% of the information using 5% of the storage. So that is how the data compression plays a role. Like we are not going very deep, we are just getting an idea. And definitely you can explore it, you can go very deep and find out exactly how it is working. But I gave you an idea. Now let us look at some real world applications of data compression. So data compression do play a role in JPEG and video streaming, visual redundancy. So the idea is that see images are matrices where nearby pixels are usually very similar, because in images nearby pixels are very similar. So what we do, how we compress it, instead of storing every single pixel, we use linear transformations like the discrete cosine transform to identify the frequencies of the image. We keep the low frequency data, that is shapes and colors, and discard the high frequency noise that the human eye can't see anyway. So the idea is very clear that how we do the data compression in JPG and video streaming, we perform linear transformation and we make use of something called as discrete cosine transform, which will identify the frequencies. And once the frequencies are identified, we will keep the low frequency data like the shapes and colors, and we will discard the high frequency noise which human eyes can't see even. And in this way, if we are eliminating some high frequency noises, we are compressing the size. And this is one of the reason a Netflix stream, it looks clear even on a slow connection. Now the second real world application is image denoising, cleaning the matrix. So see, noise, if we talk about noise in a photo, is just random, small values scattered across the matrix. So noise is something unwanted. So noise is some random small values which are scattered across the matrix, and we have to get rid of the noise. And how we can get rid of the noise? When we perform the singular value decomposition SVD, the clean image is represented by the large singular values, while the noise lives in the tiny ones. By zeroing out the small singular values and reconstructing the matrix, the noise, it disappears. And we are able to perform image denoising. And with image denoising, since we are removing the noise, we are compressing the image and we are making use of a linear algebra technique, that is the SVD, singular value decomposition. Now the next real world application of data compression is the principal component analysis, PCA. So reducing the number of variables in a data sets, like reducing from 50 health metrics to 3 health scores, is what the principal component analysis is. Now principal component analysis, it uses the same logic as the singular value decomposition to find the principal components, the eigenvectors of covariance matrix. It projects the high dimensional data onto a best fit plane, preserving the maximum amount of variance. So principal component analysis, what it does is that whatever data we have, first we calculate the covariance matrix of it, and using it we determine the eigenvectors and eigenvalues. And then we will basically transform the features into, like 50 features, we can transform it into 6 to 7 features. And out of that, only top 3 or 4 features will be relevant, containing the maximum amount of information, preserving the variance. And we just make use of that. So in this way, we are eliminating unnecessary features. And the next real world application is the latent semantic analysis, understanding text. So how does a computer know that doctor and physician are related? Because doctor and physician, they are related terms. Both are talking about something similar. So we create a term document matrix where rows are words and columns are books. By applying the singular value decomposition to this matrix, we collapse thousands of words into a few concepts. We call it the latent topics. Even if two documents don't share the exact same words, their vectors will point in the same direction in this concept space. So the idea is we start with a term document matrix and we perform the singular value decomposition of that matrix, wherein we collapse the words into concepts, the latent topics, where vectors will point in the same direction in this concept space. Now let us look at the why behind the math. See, if there was no compression via linear algebra, like without linear algebra compression, things would be very different. Phones would run out of storage. AI models would be too large to fit into computer memory. The internet would be unusable for video or high resolution images. So everywhere, data compression do play a role, and linear algebra is powering the data compression. So linear algebra data compression has got some serious applications, some serious real world applications. So linear algebra, it allows us to treat data not as a collection of bits, but as a geometric shape that can be simplified without losing its soul. So linear algebra treats data as a geometric shape that can be simplified without losing the information, losing its soul. Now let us discuss core mental model. So if we talk about data, data is the sum of geometry, which is the patterns, the algebra, some mathematical techniques, and the computations. So data is the sum total of geometry, algebra, and computation. So the core mental model is the realization that data is just not a list of numbers. Data is not just a list of numbers, but data is a shape that can be moved, that can be measured, and that can be calculated. So data is not just a list of numbers, rather data is a shape, it is a pattern which can be transformed, which can be moved, which can be measured, and which can be calculated. By merging these three pillars, the geometry, the algebra, and the computation, linear algebra, it transforms abstract information into actionable intelligence. Now let us understand these three pillars in some detail. So let us first try to understand data as geometry. So data is equals to geometry is the where. And this pillar, data as geometry, provides us the intuition. It allows us to visualize complex data sets as physical space. So rather than treating data as just list of numbers, if we treat data as vectors, then we are able to visualize the complex data sets as physical space. So space and distance. Every row in a data set is a point in a multidimensional space. if 2 points are close together, they are similar. So if we treat data as a geometry, then every data point will be a point in a space. And if they are close, if the distance between the points are less, it means they are similar. So closeness means similarity. So that is the advantage we get if we treat data as a geometry. Using the space and distance, we can find, are they similar? Direction. Vectors tells us which way the data is pointing. So vectors, they show the pointing. In AI, a word vector for king minus man plus women points directly toward the vector for queen. So what we are doing is that we are starting with a king vector, we are subtracting man from it and adding a woman. So we are talking about a women king. So women king is a queen. So we are heading towards the queen vector. So such kind of an operations we can perform if we treat data as a geometry. Because data as a geometry means we are treating data as not just as a list of numbers, but rather as vectors and matrices, the shape of data. So if we treat data as geometry, we use this geometry to find the manifold, the underlying surface that the data lives on, allowing us to ignore the empty space and focus on the patterns. So now it's very clear that if we treat data as geometry, like data is equals to geometry. So if the data is treated in the form of or represented in the form of vectors and matrices, then it will give us some special intuition. We will be able to decode the where. Like in a multi-dimensional space, the data points, the distance between the data points will give us an idea about the similarity, whether the two data points are similar. The directions, the vectors, they will help us to perform some operations on it to head towards a vector which we are seeking. And with data geometry, we can just focus on the manifold, like the underlying surfaces where the data lives on, eliminating the empty spaces or ignoring the empty spaces and just focusing on the patterns. Now let us see data is equal to algebra, the how. So it is all about the logic. Now once we represented the data, now let us suppose we have to perform some operations. How we can do that? What logic should we apply? That is what data is equals to algebra. So here we are talking about transformations. How we can transform data. So algebra, it allows us to wrap the space. If the geometry is too messy to understand, we use a matrix algebra to rotate or stretch it until the pattern becomes clear. So once we represented the data, if we see that the representation is very messy, we can perform some operations on it. We can scale it, we can compress it, we can rotate it so that we get some clear patterns. So let us suppose this is what the representation is. We can apply some linear algebraic transformations to get clear patterns which we can analyze. Now, if we talk about data is equals to algebra, we have relationships. Algebra allows us to define how variables interact. So algebra, it defines the interactions. It turns a feeling about a trend into a rigorous system of equations that can be solved. So with algebra, we can define the interactions and we can turn the interactions, the relationships into system of equations which we can solve, and the invariance. So algebra helps us finding things that don't change, that are invariant, like the eigenvalues. This is how facial recognition works. It finds the algebraic properties of a face that stays the same even if the person is in different lighting or at different angle. Because let us suppose the person, if he goes to a different lightning condition. There are many patterns, there are many features which will remain identical. And that is what invariance is. And algebra helps us to find those features which remain invariant, which does not change. And that's the power of algebra. Data is equals to algebra. So the idea is that once we represented the data, we can apply transformations on it to make the patterns more clear, more visible. We can identify the relationship and we can solve some rigorous system of equations to find the relationship, to find the interactions between the variables. And we can also find the features, the parameters which does not change, which stay invariant. So that is what data is equals to algebra. Then we have data is equals to computation, the scale, the power. So when we are talking about computation, parallelism. So unlike calculus or standard logic, which often happens step by step, linear algebra is massively parallel. You can multiply a row and a column independently, independent operations. So simultaneous operations, billions of simultaneous operations we can carry out. So linear algebra, unlike the calculus or standard logic, is massively parallel in nature. Hardware, the hardware optimization. Because the math is so structured, it makes use of matrices, vectors, the grid of numbers. Engineers, they built GPUs and TPUs specifically to do nothing but matrix multiplication. So the core idea behind the GPUs and TPUs is the matrix multiplication. Like GPUs and TPUs, they can perform billions of simultaneous matrix multiplications. And we have efficiency. Modern algorithms like the BLASH can handle matrices with trillions of entries. So this allows us to scale from toy problems to global scale systems like the Google search or the chat GPT. So the idea is very clear, like data is equals to computation. So now the data we are dealing with, because of linear algebra, we are representing the data in the form of vectors and matrices. Because of that, our data will become massively parallel, and our data is optimized for GPUs and TPUs, wherein billions of simultaneous matrix multiplications can be performed, and our data will be efficient. It can be scaled to trillions of entries, and we can transform from toy problem to global scale systems. Now let us look at the synthesis, how they power AI. Like if we combine all this together, so modern AI is the perfect intersection of these three pillars: the geometry, the algebra, and the computation. So the geometric intuition tells the researcher, I want to group similar concepts together in a 512 dimensional space. So group concepts in 512 dimensional space. The algebraic equations like the Wx is equals to B tells the model use this specific matrix multiplication like Wx plus B to move the data there. So using geometric intuition, we were able to group concepts in a 512 dimensional space. Using algebraic equations, we did some kind of a processing, we did some kind of a matrix multiplication to move the data in that space. And computational efficiency tells the hardware do these 100 billion multiplications in less than a second. And with computational efficiency, the operations, the algebraic operations, we were able to carry out efficiently in fraction of seconds. So now it's very clear that how these three pillars, the geometry, the algebra, and the computation, they are powering the AI. So if we are representing the data in the form of vectors and matrices, we are able to group it in a way we want. We can group similar concepts, or group concepts in any n-dimensional space. By applying the algebraic equations, we can transform it, we can move or change that space, move the data there. And computational efficiency, it allows us to perform operations in an efficient manner in fractions of seconds. So overall, the result is a system. We get a system that can understand language, a system that can see objects, and a system that can predict the future, all by treating reality as a massive computable geometric grid. So if we consider data is equals to geometry plus algebra plus computation, we can treat reality as a massive computable geometric grid wherein our system can understand, it can see objects, and it can predict the future. Now let us discuss the most important skill. So the most important skill is to learn to think in vectors and matrices. So we have to transform a real world problem into a matrix problem. We have to learn to think in terms of vectors and matrices. This is the most important skill. Thinking in terms of vectors and matrices is the superpower that separates someone who merely uses AI tools from someone who can architect them. So if you are someone who will be building the AI models, who will be building AI, then you have to think in terms of vectors and matrices. Thinking in terms of vectors and matrices is the superpower. It is the most important skill. It's a shift from seeing data as individual points to seeing it as a fields of influence and geometric structures. So if you think in terms of vectors and matrices, then you're shifting from seeing data from individual points to seeing the data as fields of influence and geometric structures. Now let us look at like how experts in different fields, they apply this mental framework of thinking in terms of vectors and matrices to solve world-class problems. So if I talk about thinking in vector spaces, the context skill. So experts don't see a word or an image, they see a coordinate. So the mindset is don't look at an isolated data point. Rather, think of it like a coordinate in a n-dimensional space. So the definition, so the mindset is if you are building an LLM, you don't think about definitions. You think about where a word sits in a 1536 dimensional space or where the word sits in a high dimensional space. So the idea is the mindset is when we talk about vector spaces, we are not at all looking at the values, the data, or the definitions. Rather, we are thinking in terms of coordinates, like where the data will sit in a high dimensional space. So that is the mindset. And the skill we get if we think the data or if we visualize the data in terms of a vector space, what benefit we will get is we can make use of the distance and angles. And we can make use of the distance and angle to find the related data points. So an expert knows that if two vectors have a high cosine similarity, then they are pointing in the same direction, regardless of the spelling. The underlying concepts are related, regardless of how they are spelled. That's the idea. So if we consider the data, or if we think the data in terms of vector spaces, then we are not talking about the numbers, we're not talking about the definitions, but we are considering the coordinates. Like we are talking about where the data is sitting in high dimensional space. We can make use of distance and angles to calculate cosine similarity. And if two vectors have high cosine similarity, it means they are related. So it means we are talking about related concepts regardless of the spelling. Thinking in terms of matrix transformations, the action skill. So matrix transformation is the action skill. So in robotics and computer vision, experts don't think about moving an arm or rotating a photo. They think about wrapping space. So a robot arm moving from point A to point B is just a series of matrix multiplications. So the idea is, if we think in terms of matrix transformation, then any operation, any action, we treat it like a series of matrix operations. And in this way, we are visualizing the basis change. An expert can see how multiplying a vector by a matrix changes the camera view or the coordinate system, allowing the robot to understand where its hand is relative to the cup. So, if we think in terms of matrix transformation, we are actually visualizing the basis change. Mathematically, we are able to determine how much we changed or how exactly the robotic arm moved relative to the any object. So we have to think in terms of matrix transformations. Any action, we have to think in terms of matrix transformations. Thinking in terms of projections, the simplification skill. Optimization and data science experts, they are masters of shadows. So real world data has too much noise. An expert asks, what is the 2D shadow of this 100 dimensional problem? So that is what the simplification skill is. So we should think in terms of projection. So the idea is that high dimensional problem, we have to convert it into a low dimensional problem. So that is what the dimensionality reduction is. So here we are talking about the dimensionality reduction. So we should think in terms of projection. And the skill for that is dimensionality reduction. We should strip away junk. Make use of projection to strip away the junk variables, leaving only the principal components that actually drive the results. And then we have thinking in terms of decompositions, the diagnostic skill. So how we can think in terms of decomposition. So first let us understand what is the meaning of it. Thinking in terms of decomposition. So this is the highest level of thinking, taking a complex, messy system and breaking it into its pure mathematical DNA. So thinking in terms of decomposition means a massive matrix of user data, we break it into a combination of simpler hidden patterns. So massive matrix is equals to combination of simpler hidden patterns. So we break or we decompose a messy system into pure mathematical DNA, smaller matrices. So that is what the decomposition, thinking in terms of decomposition. Now the skill for that is the singular value decomposition or the eigen decomposition. We can look at an expert looks at a confusing matrix and thinks what are the eigen vectors, the fundamental directions, and the eigen values, the strength of those directions of the system. And using this information, they break the complex system into smaller subsystems. That is what the thinking in decomposition is. So now it's very clear that we should think in terms of vector spaces. So here we are talking about the context skill, and distance and angles are the tools for us. We should think in terms of matrix transformations, the action skill, and the tool is to visualize the basis change. We should think in terms of projection, the simplification skill, the tool is to do the dimensionality reduction. We should think in terms of decomposition, the diagnostic skill. The tool is singular value decomposition, principal component analysis, or the eigen decomposition. Now, let us get a realization why thinking in terms of vectors and matrices is the most important skill. Why it is the superpower. So see, if you only know the code, you are a passenger. But if you think in linear algebra, you are a navigator. So you see, the idea is that if we just focus on the code, we are just a passenger. Passenger means we don't know what is happening, how the system is working, or how the driver is driving the vehicle. If we just know the code, we are just calling some inbuilt functions. We don't know what is happening in that inbuilt functions. But if you think in terms of linear algebra, then you are the navigator. You will be designing those inbuilt functions. You will be leading that in which direction should we move. You will become the navigator. So why thinking in terms of vectors and matrices is important? It is important for debugging. Let us suppose a model fails. When a model fails, you don't just try more data. Rather, you will look at the rank of your matrix to see if your data is redundant. Scaling, you understand why a GPU is fast and how to structure your math to take advantage of it. Because if you think in terms of vectors and matrices, you have got the in-depth knowledge of how exactly the model is working. You can debug the model, you can scale it, you can make the efficient use of the GPU. You know that you have to convert the problem into the matrix problem because GPU is made for matrix multiplication. You can structure math for GPUs and the innovation. Every major breakthrough in AI, like the transformer architecture used in ChatGPT, was born from someone finding a new way to multiply and attend to matrices. So any innovation will be in terms of vectors and matrices. So now it's very clear to us the importance of thinking in terms of vectors and matrices. We can get to know how the model is working. We can debug, we can scale, and we can innovate our model. So if we can summarize this, the expert's fluency. So in traditional thinking, we say like if price goes up, sales go down. But in vector and matrix thinking, the same statement we say that negative correlation vector in feature space. Because if one feature is increasing, the other is going down, it is a negative correlation. In traditional thinking, if we make statements like rotate image 90-degree, in vector and matrix thinking, we say apply rotation matrix to the pixel grid. In the traditional thinking, if we say the statement like find the most important factor, in vector and matrix thinking, we say find the eigenvector with the largest eigenvalue. Now let us look at some real world examples where linear algebra appears daily. So we will look at the application, the linear algebra tool, and the connection. So if we talk about the Google search, application is the Google search. Now Google search, it makes use of eigenvectors in its page ranking algorithm. So how does importance relate to vector direction? Now if we talk about the application of face recognition, in face recognition, we make use of the principal component analysis, wherein we reduce the complex faces to essential eigenfaces. In the ChatGPT embeddings application, we make use of the vectors, semantic space. So we represent the words as vectors as points in the high dimensional space. In the Spotify recommendations application, we make use of matrix factorization, the collaborative filtering. We decompose the user item matrix to find hidden patterns. In image filters, we make use of the linear algebra tool called the convolutions, kernels and matrices. So in convolutions, we slide a small matrix over an image and we perform some specific operations like we detect edges, blur, and the next application is the robotics. So in robotics, we make use of transformations. The linear algebra tool is a transformations. like the matrices and the kinematics. So moving robot arms use rotation and translation matrices. So these are like some real world examples where linear algebra appears daily. Now let us look at why large matrices matter. Why large matrices matter? See, modern data is huge. In the early days of computing, we dealt with toy problems, a few dozen data points that a human could check with a pencil. Today, matrices aren't just larger, they have reached a scale where they exhibit entirely different mathematical behaviors. So, so basically, the idea is that we have transformed from toy problems to scale driven intelligence. So now let us see why the transition to the large matrices changed the world of technology. So first let us look at the scale of reality. So modern data sets, they are wide, they contain many features, and they are tall, many observations. So the modern data set, it is massive, wherein it has got lots and lots of features. It is wide, it contains many features, and it is tall. It contains many observations. So the world we are in, we are talking about millions of users. A recommendation matrix for Amazon or Netflix, it is not just big, but it is sparse. Meaning to say that millions of rows and columns are empty. Like 99% of that matrix might be empty. So a recommendation matrix used by Amazon or Netflix is 99% empty. Now linear algebra provides the tools like the sparse matrix storage to handle this without crashing the system. Now, the world we are living in, we are talking about billions of parameters. The large language models, like the GPT-4, they are essentially trillions of numbers organized into matrices. So, these large language models are basically the trillions of numbers. Every word generated is the result of these massive grids interacting. So every word generated by a large language model is a massive grid interaction. The world where we are living in, we are dealing with high dimensional data, high dimensionality. In biology, a single DNA sample can have 1 lakh plus variables. And that is what the curse of dimensionality is. Because 1 lakh plus variables or samples is where the traditional statistics break down. And here, high level linear algebra comes into the picture. We make use of dimensionality reduction to reduce the dimensions. And for that, we make use of high level linear algebra that can find the signal in the noise. So now it's very clear if we talk about the scale of reality, the real world where we live in, we are dealing with, the systems are dealing with millions of users, billions of parameters, and high dimensionality. And linear algebra is playing a role. And also, we are realizing the importance of large matrices. Why do we need large matrices? Now, the next important point is the four massive challenges. The four massive challenges. So, the first massive challenge is the computation challenge, the work problem. So, standard matrix multiplication takes big O of n cube time. If you double the size of a matrix, the work does not double, it increases eightfold because it's n cube. Now the goal is we need algorithms like the distributed computing that can cheat the physics of computation to get answers in seconds rather than years. So for that we need large matrices. So computation is a very big challenge. So now the idea is very clear that if we are dealing with large matrices, computation is the bottleneck. Like we see that the traditional matrix operations, the standard matrix operations, they are the order of big O of n cube. So we need some sort of distributed computing algorithm, some techniques wherein we can optimize the computations. Now, the second very big challenge, the massive challenge is the memory, the space problem. A matrix of 100K cross 100K array, floating point numbers would take roughly 40 GB of RAM. Just imagine if we are dealing with a very big matrix of 100K into 100K, and this matrix is holding floating point numbers, then it will occupy 40 GB of RAM. It will need 40 GB of RAM, which can be very huge. So experts, they make use of matrix factorization and quantization, turning 32-bit numbers into 8-bit or even 4-bit to shrink the footprint of the matrix so that it can fit on a smartphone or a single GPU. Now the third massive problem, the challenge, is the speed, the latency problem. So for self-driving cars or a real-time translation, the speed can be a bottleneck. The math must happen in milliseconds. So if for real-time systems and for self-driving cars, the math must happen in milliseconds. So the goal is real-time parallelization. So large matrices matter because they are perfectly suited for GPUs. GPUs can carry billions of simultaneous computations. So GPUs can calculate thousands of dot products at the exact same time. And the fourth massive challenge is the numerical stability, the accuracy problem. When you multiply a billion small numbers together, rounding errors, they might explode. A tiny error in the 10th decimal place can snowball into a completely wrong answer. So rounding errors might explode. So the goal is we use advanced decomposition like the QR to ensure the computer stays stable and the AI does not start hallucinating due to math error. So that is the idea. So these are like the four massive challenges when dealing with the large matrices: the computation, the memory, the speed, the numerical stability. And we make use of large matrices to deal with this problem. And linear algebra has got the tools for it to deal with these four massive challenges. Now let us look at the shift in the perspective. So basically, we have seen a shift in the perspective, like from calculating a result, calculating individual numbers, to architecting a system. When we are dealing with large matrices, we stop worrying about individual numbers and we start worrying about the flow. We learn to treat a matrix like a massive pipeline of information. So large matrices, we should treat it like a massive pipeline of information. So clogged pipe is slow AI. So if the pipeline is clogged, inefficient, the AI will be slow. If the pipeline leaks, the pipeline is unstable, then the AI is dumb. So the bottom line is we don't study large matrices because we like big numbers. We study large matrices because scale is where intelligence emerges. So we study large matrices because scale is where intelligence emerges. So now the idea is very clear that the modern data is huge and we have to go for large matrices. And the good thing is that the modern AI hardware, the GPUs, the TPUs, they support large matrices. They can carry out billions of matrix operations simultaneously. And when we consider large matrices, we are thinking, or we are considering the complete system. And scale is where the intelligence emerges. So this is the importance of large matrices. So finally, we completed this lecture. In this lecture, we saw that linear algebra is the language of data, the engine of AI, and the mathematics of modern computation. We saw the master equation, the central equation of linear algebra, Ax is equals to b. And we also looked at the core applications of linear algebra, like in neural networks, in optimization, in compression, and in machine learning. I hope you got a very good understanding of the concepts that we covered in this lecture. So do subscribe to our YouTube channel Scale Up University for more such interesting lectures and courses. Thanks for watching. Thanks for your time.